Most developers treat LLMs as sophisticated text predictors. Input a string, get a string. But text is a bottleneck. The real world doesn't live in a text box. It lives in a complex UI layouts, dense documents, and physical spaces. Today, we are moving beyond the prompt and giving our agent eyes. We aren't just building a chatbot that describes images. We are building a system that can interpret a visual state and execute a precise action based on what it sees. This is the transition from descriptive AI to a prescriptive implementation. To build with vision, you have to understand the backbone. GPT-4o doesn't see a JPEG the way you do. It uses a process called patching. The model takes your image and chops it into discrete visual tokens. These tokens are then fed through a multi-modal projector that aligns visual features with the language space the LLM already understands. This shared mathematical space is why the model can reason about the relationship between a submit button and the input field next to it. It's not magic, it's a high-dimensional alignment. In production, resolution is your biggest variable. You have two modes, low and high. In low detail mode, the model sees a 512 by 512 summary for a flat cost of 65 tokens. It's fast, but it's blurry for detail-oriented tasks. In high detail mode, the model tiles the image into 512 pixel squares. Each tile costs 170 tokens plus an 85 token base. If you're building an agent to perform OCR or find a specific 20 pixel icon on a 4K screen, you must use high detail. If you don't, your agent will hallucinate coordinates because it simply can't see the pixels it's trying to click. The hardest part of vision implementation isn't identifying an object, it's grounding it. You don't want your model to say I see a button. You want it to say the button is at XY coordinates. Because models are trained on various aspect ratios, we use normalized coordinates, usually on a scale of 1 to 1000. This makes the output resolution independent. When the model returns a point, your code can then map that back to the actual pixel dimension of your browser or mobile device. This is how we bridge the gap between pixels and Python. As builders, we have to talk about the risks. Vision introduces a new attack vector, visual prompt injection. An image can contain hidden, high-contrast text or adversarial noise that overrides your system instructions. If your agent is looking at a user-uploaded document, that document could literally tell the agent to delete all files. Your implementation must include visual sanitization and output verification. Never allow a vision agent to execute high privilege command without a secondary logic check in your code. Precision building requires defensive building. Now it's time to get hands-on. Let's open the terminal and create a new folder. Move inside of it and create a new virtual environment. Activate the virtual environment and let's install two dependencies. The first one is OpenAI for the model interface and Python.env for secure credential management. After the dependencies have been installed, we create a new file called .env and here we put our OpenAI API key. Next, we create our main.py file. Our first task is bridging the gap between a local image and the API. GPT-4o doesn't accept raw binary. It requires a base64 encoded string wrapped in a data URI. We define the encode image function to read the file in RB or read binary mode. We then use the base64 library to transform those bytes into an UTF-8 string that the LLM can digest. Without this step, the model is effectively blind to your local data. We are going to wrap our logic in a vision agent class. This is about maintainability. In the constructor, we initialize our OpenAI client. By abstracting this into a class, we can easily swap the models or add persistent memory later. We are defaulting to GPT-4o because we need its native multi-modal capabilities for spatial reasoning. This is where the implementation gets serious. We create an analyze UI method. Inside of this method, notice the message structure. We aren't just sending a string, we are sending a list of content objects, one of our system instructions and one of the encoded image. Crucially, we set response format to JSON object. This forces the model to return structured data rather than conversational fluff. We are also setting detail to high. This triggers the 512 pixel tiling we discussed earlier. This ensures the model can actually see the UI elements we are targeting. And finally, we instantiate our agent and run a test. We will pass it a screenshot of a dashboard and ask it to find the export button. For testing this, I have prepared this screenshot PNG file. You can see that it represents a simple dashboard with the export to CSV button. Now it's time to open our terminal, clear the previous output and run our main.py file. As you can see, the LLM is analyzing the UI. You can see how smart it is. It was able to find the export to CSV button with its precise coordinates. If you're interested, you can calculate this on your own machine and see if the LLM was correct. We have covered the architecture of vision, the token cost of high detailed tiling, and the logic of spatial grounding. We have moved from the theory of multimodality to working implementation of a visual inspector agent. Remember, vision is the bridge that allows your code to interact with the world exactly as it is, not just how it's described in text. The complete source code for this builder session is in the description. If you're ready to stop watching and start building, subscribe to ByteBuilder. I'll see you in the next one.